Hello everyone, and welcome to Chapter 3 of your linear algebra course, Linear Systems. We will start with section 3.1, also entitled Linear Systems. The goal of this section is to define linear systems and their solutions. In section 3.1.1, we first consider linear equations. Definition 3.1.1 gives us the definition of a linear equation. A linear equation in the variables x1, x2, all the way up to xn is an equation of the form a1x1 plus a2x2 plus all the way up to anxn equals b, where the coefficients a1, a2, all the way up to an, and the constant term b are real numbers. So this is what a general linear equation looks like. In example 3.1.1, we are asked to determine which of the following equations are linear. In part A, we have the equation 2x minus 3y plus 2z equals 6. This is the equation of a plane, and we've seen many equations of planes in Chapter 2. Is this equation linear? Well, the variables in this equation are x, y, and z. Each variable is multiplied by a real number, and there's also a constant term, the 6. The equation is linear. In part B, we have x squared minus y cubed equals 0. This equation is not linear because the variables in a linear equation are not raised to a power other than 1. And here we have x, one of the variables, raised to the power of 2, and y, another variable, raised to the power of 3. So part B is not linear. In part C, we have x1 minus x2 plus 3 times the square root of x3 equals minus 7. In this case, we have a term with the square root of x3, the square root of one of the variables of the equation. Recall that the square root of x3 can also be written as x3 to the power of 1 over 2, which again is a power other than 1. And so the equation in part C is also not linear. In part D, we have the equation 3y minus 2z equals 14 minus x. The variables of this equation are x, y, and z. What we have here is an equation in which there are variables on both sides of the equal sign. Now if we add x to both sides, we get x plus 3y minus 2z equals 14. And once again, this is the equation of a plane, and so part D, the equation in part D is linear. Moving on to part E, we have pi over 4 times x1 minus sine of 2 times x2 equals the square root of 3. Now the two variables here are x1 and x2. Pi over 4 and sine of 2 are real numbers, multiplying the variables. And we also have a constant term of the square root of 3. This equation is also linear. In part F, we have 2w minus 3z plus 6xy equals 9 plus log of x as our equation. There are two things to notice here. We have the term 6 times x times y. In a linear equation, variables should not be multiplied by each other, only by constants. Also, the second thing to notice is that we have the term log of x. And so one of the variables is an argument of a nonlinear function, which is impossible for a linear equation. And so in part F, the equation that we have is also not linear. Let's summarize our findings. An equation is linear if the exponent on each variable is 1. The variables are only multiplied by constants, and the variables are not arguments of a nonlinear function. In definition 3.1.2, we define the solution of a linear equation. The vector with components s1, s2, all the way up to sn is called a solution of the linear equation a1x1 plus a2x2 plus all the way up to anxn equals b if it satisfies the linear equation. That is, if a1s1 plus a2s2 plus all the way up to ansn is equal to b. That is, if you plug in the components of the vector s1 to sn into the variables x1 to xn, add up all the terms on the left-hand side, you will get b. One thing to remark is that the solution vector, s1, s2 up to sn, can be thought of as the position vector of the point s1, s2 up to sn. When interpreting the solution of a linear equation geometrically, we commonly refer to it as a point rather than a vector. In example 3.1.2, part A, we want to show that the vector 3 minus 1, 2 is a solution of the equation x plus y minus 3z equals minus 4. We will plug in 3 minus 1 and 2 for x, y, and z on the left-hand side and see if we obtain minus 4. So 3 plus minus 1 minus 3 times 2, that's equal to 3 minus 1 minus 6. 3 minus 7 is equal to minus 4. So the vector 3 minus 1, 2 satisfies the equation x plus y minus 3z equals minus 4. It's therefore a solution of that linear equation. In part B, we want to show that for any t in R, x equals 1 minus 3t, y equals t is a solution of the equation x plus 3y equals 1. This potential solution is presented to us in a different form, in parametric form. Again, we're going to plug in x and y into the equation on the left-hand side and see if we obtain the right-hand side, 1 in this case. So x is 1 minus 3t plus 3 times y. Y is equal to t. 1 minus 3t plus 3t is equal to 1. And so for any t and r, x equals 1 minus 3t and y equals t is a solution of the equation x plus 3y equals 1. In the next video, we'll define systems of linear equations.